Hello. In the previous examples, you know exactly what you were supposed to prove. But sometimes, in some situations, you will not really know the final statement. You will have to do some computation or some guessing work first. But don't worry, this example will be easy, and in the next video we will have a similar example, slightly more difficult, which you can try to solve yourself. Let's start. Sequences. Guess and prove. Problem number 2. And this is a problem. Find the formula for an, for a sequence an, if a0 is equal to 1 and a with index n plus 1 is equal to twice an, for n equal to 0, 1, 2, and so on and so on. So you see here that we have some sequence which is clearly called an, and we know the first element of this sequence, and we don't really know the others, but we know how the next one is expressed with help of the previous one. So this type of definition is called a recursive formula for the sequence, and we are supposed to give an explicit or closed formula. So now I will start solving this, and then I will show you which one will be explicit formula and then how to prove it. You know, of course, by induction, right? Okay, so first let's start working with this sequence. So this sequence will be A0, A1, A2, A3, and so on and so on. But by now you don't really have a formula for each element an, but you know how the next one is produced from the previous one. Here is a recipe for this. And now let's try to find out what this closed or explicit formula will be. Okay, first will be a0 is equal to 1. Here we don't have to guess anything, it is simply given to us, right? Then, by this definition here, with n equal to 0, we will get the expression for a1. You see this, right? If I now plug in n equal to 0, then I will get a0 plus 1, this is a1, is equal to twice a0. But a0 is given, it is 1. So a1 is equal to 2. Now I have already a1. And what about a2? a2 will be given by in the following way, if I plug in n equal to 1 in this formula here. So I will get a2 is equal to twice a1, right? But I know already from the previous step that a1 is equal to 2. So it will be 2 times 2 is equal to 4. So I have already a2. And already now you can start guessing, right? Because here the expression for a2 is 2 squared, right? The expression for a1 is 2 to the first. And the expression for a0 can be written as 2 to 0, because you know that each non-zero number raised to the power 0 gives 1. So you have actually probably guessed what t of n will be, right? T of n is the following, that an is equal to 2 to the power n. This is what I have guessed by observing how the next elements of my sequence look. And this is a closed formula or explicit formula. This means that if you have to compute, let's say, a10, then you don't have to go to all the previous elements and go through this procedure, but you can simply plug in 10 instead of n, and you will get that a10, here in this case I will write down, for example, a10 is equal to 2 to the power 10, it is 1024, right? So this is a closed formula, the formula which only depends on n. When you have n, you can compute an. Instead of going through this entire chain of previous elements. So now we do have our T of n, which we have to prove. And sometimes, of course, it can happen that your guess is wrong. But here it just looks right, because you see that each time we have to double the previous one. So if the first one was 1, then we have 2, 4, 8, 16, so it's clear it is a correct guess, right? But in some more difficult cases you can get a wrong formula, and then your induction proof will not work. Okay, but now we start proving our formula. The base case, t of 0 will look like this, that a0 is equal to 2 to 0. And this is true because by definition a0 is equal to 1. So this one is okay. And now the next step is we have to write down the thesis for n plus 1. Well, it is easy. A n plus 1 is equal to 2 to n plus 1, right? And now we have to, the last step is the induction step. We have to show that if we assume that t of n is true for some n which is greater than or equal to 0, then t of n plus 1 is also true. So let's assume that t of n is true for some n which is greater than or equal to 0. And what is this t of n? Here, this is such a short formula that I can copy this here. This means that an is equal to 2 to n. We assume that this is true for some n. And we have to show that this proves, we must show that this implies that t of n plus 1 is also true. And what was our t of n plus 1? T of n plus 1 was that a n plus 1 is equal to 2 to n plus 1, right? So now this green one is our assumption, and we have to prove this orange one. And what do we have? We have our definition. We know how an plus 1 depends all on an. So from the definition of our sequence, we have an plus 1 is equal to twice an. So this is from the very definition. But now I can use the induction assumption. So here I will use induction assumption. And what was this assumption? That an is equal to 2 to n, right? Because we assumed that t of n is true. So here it will be 2 times 2 to n. But of course, 2 to n times 2 is equal to 2 to n plus 1, which is exactly what we were supposed to show. This is the statement that t of n plus 1 is true. And this means that according to the, and now I will just write the principle of mathematical induction, PMI, the statement t of n is true for all natural n. And that's all. We are done with this one. So you see, from this recursive formula, we kind of guessed the explicit or closed formula, and then we verified this by induction that it is indeed the true formula, that we didn't do a wrong guess. And in the next video you will have a similar problem, but slightly more difficult. Thank you for watching. Bye bye.